Right, okay, this should be recording now. I'm looking at question 8, exercise 7C. In the previous video, I used a table to summarise things. This question here lends itself to a tree diagram, which I'm going to draw in a minute, so that we can try and work out what the probabilities are for this game. So we've got 5 red cards, 4 blue, 3 green. If you add all that up, you have 12 cards in a box of some description. It's not a see-through box. So you randomly draw out a card. If you get 3 cards, where is this? Here. If I get 3 cards that are all the same colour, or if I get 1 red, 1 blue and 1 green, and the order doesn't matter there, then I win $11, and that's why it's called Lucky 11. Okay, tree diagram time. I'm going to use a tree diagram as a way of thinking about these probabilities. So this can be like the start of my game over here, and I could draw out a red, a blue, or a green. Okay. Now, there were 5 red cards out of 12. There were 4 blue cards, and there were 3 green. Now let's consider the pathway where you got all reds, right? So on the next draw, say I got another red, and then I got another red, because that would be a way to win the game. What's the probability of getting a red, and a red? All right, well on the next draw, there's only 11 cards left, right? Because I carefully read the question and it said that the cards are drawn without replacement, right? So on second draw, it doesn't matter where I am on the tree diagram, but there'll only be 11 cards left. And one of the red ones is gone, so there'll be 4 out of the 11 cards will be red. And then on the third draw, there's only 10 cards left. One of the red ones is gone, it's not been replaced, so there'd be 3 out of 10 would be red. And to work out the probability, I would need to multiply. It's like an AND statement. I want to get a red and another red and another red. We're multiplying. So this probability is 5 out of 12 times 4 out of 11 times 3 out of 10. Okay, so 5 times 4 is 20. 20 times 3 is 60. What out the bottom? 12 11s, that's 121. No, it's not. It's 132. 132 times 10 is 1,320. Okay. Now I'd need to consider, what if we got a blue followed by another blue, followed by another blue? That's another way to win the game and get $11. And I also need to consider 3 greens. So we got a green followed by another green, followed by another green. What's this probability? GGG. All right. Okay. Well, you started with 4 blues, but you've drawn 1 on this path. So there's only 3 left. There's 11 cards left. On the next draw, you'd have 2 out of 10. With the greens, you start with 3 greens. Right, that drops down to 2 because one of these greens is gone. Then it drops down to 1. Notice how the second draw, there's always 11 cards left. So it's always out of 11. On the third draw, there's always 10 cards left. It's always out of 10. Right? So here we'd have, I think I'll just go to the answer. 4 times 3 times 2. 4 times 3 is 12. 12 times 2 is 24. All right. Notice how it's always going to be out of 1,320. And along this pathway, I'd have 3 times 2 times 1. So it'd be 6 out of 1,320. Now there's another way you can win the game. You can win the game if you get a red, green, or a blue, or a blue, red, or a green, or a green. You know, the order doesn't really matter, but you need to get one of each colour, right? I wonder if I can fit it in here. So what if I got a red, followed by a blue on the second draw, followed by a green, right? So put in another path on the tree. The probability that I got red, then blue, then green. We could also get blue, then red, then green. Or we could get blue, then green, then red. We could get green, red, and blue. Here we could have gone red, green, and blue. So we've got a few different paths in our tree that we need to be thinking about. You could have the probability that you went red, green, then blue. Right. You could have somewhere along here, maybe I'll draw in one of them. What if I went green and then went red and then blue? All right, so that's one option. Probability that you've got green, then red, then blue. You could also have green, then blue, then red. Still missing a couple. If I start with the blues, I could have probability of blue, red, green, or probably, if I just sneak this one in here, blue, green, red. All right. So each of those paths through this tree would give a win of $11, right? And there's an extra 6, right? So these, that one, 2 there, and 2 there. Now the good thing about these is the numbers will always be the same. If I just calculate, maybe I'll pick 2 at random. If I pick this one here, and let's pick this one down the bottom, and you'll see that the values will come out the same because the order of multiplication doesn't matter. So to get a red on the first draw, we've got 5 out of 12 as our probability just for that first step. Then to get a blue on the second draw, well, it's out of 11 and there's still 4 blue cards left. 4 out of 11. And then green, all the greens are still left. There's 3 of them and it's out of 10 cards. Right, so that works out to be, it's the same numbers as this, so it'd be 60 out of 1,320. Now going along this way, your calculation would be 3 out of 12, right, to get green first, 3 out of 12. Then say you went red, well you've got all the reds still there, 5, and it's out of 11 cards because you're not replacing. Then you got a blue, you'd have 4, all the blues are still left, it's out of 10. Now the order that we multiply doesn't matter, so doing 3 times 5 times 4, that's the same as doing 5 times 4 times 3, right? And the bottom part of the fraction, the denominators are the same as well, so okay. So we'd end up trying to put all this together. We've got Where can I draw a table for this? Maybe down the bottom. We've got these values as ways of winning down here. Probability that x equals a specific value. Well, what's the red, red, red? And the blue, blue, blue. I'm just listing all the wins, really. The green, green, green. What if we did the blue, blue, red, green, but order doesn't matter. So any order, any order. Okay. So for red, 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 it was 60 out of 1, 3, 20. Blue, blue, blue was only 24, it was less. And green, 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 the odds of that happening are quite small, 6. 1, 3, 20. Now there were 6 ways to get one of each colour, and every time we did that, that was the probability. So you've got 6 times 60 on 1, 3, 20. And that's all your wins. And I'm going to do some erasing and try and summarise all of this. So I'm getting rid of my tree diagram because I've running out of room here. But hopefully you can see how the tree diagram was pretty useful. I just want to think about a win. Do I win $11? A win? Or do I lose the game? A loss. Right? Because a loss will just be the rest. Right? If I was to extend this table out, it's like all the other pathways, through the tree, they're a loss, right? And that would have to be 1 minus all of the wins, right, to get the probability. Because it would have to add up to a probability of 1 to represent 100% or all of the pathways. The probability that I get a win or a loss. Okay. So a win can come from those plus these 6 here. All right, well, these 6 here, that's 6 times 60 is 360, plus another 60, that's now I'm up to 420, plus 30, there's 450 pathways out of 1, 3, 20, right? And the loss is all the rest, And so I don't make a mistake, I think I'll go to a calculator for this one. 1, 3, 20 minus 450. So what do we got? 1, 3, 20 minus 450. There's 870 left. All right, so I'm just double checking my numbers. 870. Oh, need a pen to work. 870 out of 1, 3, 20. Now, if you win, you get, so your winnings, if you win, you make $11, but if you lose, you make $0, okay? All right. Now the expected value, let's just calculate. Imagine you didn't have to pay any money to play this game, right? So there's going to be a fee to play this game, but let's pretend there isn't just for a minute, all right? You would have an expected value of 450 wins out of 1,320 times $11, all right? So you'd have 450, a probability of 450 right, times that win of $11. Right. Now I'm going to go for the calculator again here. So what do we get? 450 times 11. Sorry, I'm still on my pen tool. 450 times 11, which is 4,950. 4,950. 4,950 out of 1,320 schmackaroos or dollars. Right, so on average, I don't know, what does that looks like? About $4 maybe per game. 4,950 out of 1,320. 4,950 divide. No, it's not going to let me do that. Sorry. Back again. Divide 1,320. $3.75 per game. Right. That worked out quite nicely. $3.75. Okay. Now I'll make a bit of room down the bottom so that we can finish the question because I can't remember what it's asking me to do next. I think it wants a winning of $1. Right. The organizer wants to make an average of $1 per game. Right. Okay, so they don't want to lose $3.75 every game. They want to win $1, right? So how are they going to do that? Well, they're going to have to charge $4.75, right? So if you want your expected value here, it needs to be minus $1. Right? So that's from the perspective of you playing the game. So you're going to play the game, and on average, you're going to lose $1 every time you play that game. And I don't really think we need to do too much else with this question because you can kind of see, well, if the expected value starts at $3.75, given that you didn't put any money in, but really you want to get it to there, well, what's the difference, right? And the answer is $4.75, okay? So hopefully that's not confusing you too much. Let me just run through it one more time. If the game was free, right, you'd be up $3.75. But the organizer doesn't want you to be there. They want you to be at -1 on average, right? So they need to charge you $4.75. So you start this game with paying $4.75. You only get $3.75 on average, right? You probably have to play the game 100 times for that to happen. And so then on average, you would lose $1 per game, right? Okay. Let me know in the comments or by email if that wasn't overly clear, the last bit. Okay, thank you.